The paper discusses the application of pre-trained architectures, such as convolutional neural networks, CNNs, and vision transformers, ViTs, for periocular recognition. These models have been successfully used in various computer vision tasks beyond their original purpose. The authors extend their previous study on using off-the-shelf CNNs and include the more recently proposed vision transformers. They demonstrate that CNNs and ViTs are highly complementary, as their combination results in boosted accuracy. The paper also shows that a small portion of these pre-trained models can achieve good accuracy, resulting in thinner models with fewer parameters, suitable for resource-limited environments. This efficiency improves if traditional handcrafted features are added as well. The authors use the UBIPR database, which contains images taken with varying distances and resolutions, and manually annotate them for pupil and sclera circle parameters. They resize images to match the average sclera radius and align them by extracting a square around the sclera center. The authors compared 3 CNNs and 3 ViTs with varying depths and parameters to analyze the impact of network complexity. They also explore different methods to normalize layer representations. They eliminate the advantage observed in previous works where left and right eye images were compared directly, instead flipping images of one eye horizontally to align the orientations and shapes of the overall eye structure. The authors use vectors from intermediate layers as feature descriptors and compare them via cosine similarity, a common method in biometrics. They evaluate several normalization possibilities, including L2 normalization per patch, per channel, of the entire vector, and averaging across channels or patches. They also use traditional handcrafted features such as LBP, HOG, and SIFT as baselines, showing that these features can benefit the recognition mission when combined with CNNs and ViTs. The research paper presents an investigation into the representation capabilities of convolutional neural networks, CNNs, and vision transformers, ViTs, for periocular image verification. The study employs various vector normalization techniques, including L2 normalization per channel, per patch, and entire vector, to examine their impact on verification accuracy. The experimental results, as shown in Figure 3, demonstrate that L2 normalization per channel yields the best verification accuracy, particularly with CNNs. Averaging feature vectors across channels or patches reduces recognition accuracy, suggesting that such integration methods are ineffective. The best performing layers for each CNN and ViT are reported in Table 2, with ResNet 50, R50, providing the best accuracy, EER equals 8.53%, followed by ResNet 18, R18, and ResNet 101, R101. Analysis of the learnables in Figure 4 reveals that R50 and R101 have comparable parameters up to layer 150, which may explain their similar local minima. The smaller R18 has fewer parameters, but its performance is only 0.7% worse than R50. In contrast, the best performance of ViTs occurs in the first half of the networks, with the tiny ViT achieving similar performance to the small and base ViTs with significantly fewer parameters. Fusion results using L2 normalization per channel are presented in Figure 5, showing that combining scores from multiple comparators improves verification accuracy. The paper proceeds to investigate the effectiveness of L2 normalization per channel in the remainder of the study. The findings suggest that while CNNs require most layers for optimal performance, ViTs achieve sufficient abstraction earlier, and deeper layers degrade performance. This research paper investigates the use of pre-trained convolutional neural networks, CNNs, and vision transformers, ViTs, as feature extraction methods for periocular recognition. The authors analyze the behavior of each network layer and evaluate the complementarity between CNN and ViT features through fusion experiments. The results show that the best fusion cases usually involve the optimal CNN layers or those nearby, and that the ViT layer employed in the fusion is not as critical as the CNN layer. The study also explores the use of traditional features, including local binary patterns, histogram of oriented gradients, and scale invariant feature descriptors, which are found to complement the recognition task effectively. The authors observe an upper limit in the number of CNN layers and parameters needed for optimal performance, and that larger pre-trained models are not advantageous. The lighter versions, R18 CNN and Tiny ViT, perform sufficiently well with significantly fewer parameters. The paper further discusses the implications of the findings, including the importance of not averaging feature vectors across channels or patches, and the potential benefits of incorporating other CNN architectures that may be complementary to the present ones. Future work includes analyzing the observed complementarity of the models, extending the research to infrared data or other biometric modalities, and incorporating other CNN architectures. The results of this study have significant implications for periocular biometrics, highlighting the effectiveness of using pre-trained CNNs and ViTs as feature extraction methods and the importance of considering the complementarity between different models. The findings also underscore the need for further research into the optimal use of pre-trained models and the potential benefits of incorporating traditional features and other CNN architectures.